We're continuing with sequences here in 9.1b. We're going to start off with the idea of a recursive formula. So in other words, the sequence is going to be defined by something that depends on the number that came before it. Now, let me show you here. So we're told here in this one that A1, and we're going to have to define the terms because the order is going to matter here. So we're going to say this is the first term in the sequence. The first number is 1, or the first term, when A is 1, I should say, when N is 1, is 9. Now, every term that comes after that is going to be dependent on the value that we got in the previous iteration. So let me show you what I mean. When N was 1, we knew we had 9. When N is 2 now, it's going to be based, this represents the number before us. So the number before us was 9. So we're putting 3 times 9, that first value that we got, minus 20, crunch it down. Now look what happens when we go to 3. We've got 3 times the number that was before us, which this time was 7. So we're going to be dependent on the value that we got in the previous iteration. So we crunch it down, we get 1. Now, so when N is 4, we're putting in, we need, what was the value for A3? Well, A3 is the one we just created, it's 1. So we've got 3 times 1 minus 20. You see how we keep being dependent upon the value that we created in the last iteration. So I've got 3 times A4. A4 was negative 17. We crunch it down. We get negative 71. Okay, so the same concept here. You can pause it and try this if you want to do it on your own. But so we've got when N is 1, we get A1 is 2. When N is 2, we get A2 is 2 times what we got in the first iteration, which is 2. So this is going to turn out to be 5. Okay, now round 3 here, we get A3 is going to be 2 times what we got in the last round, which is going to be 5 for us. It was this number, plus 1, we get 11. How many terms do we want? 5 of these. Okay, so we want A4, 2 times what we got in the last round. In the last round we got 11. So 22, 23. And then lastly, when N is 5, okay, I've got 46, I got 47. Okay, if they're asking for the first 5 terms, we really probably should put them in set notation like this, but you'll see those match up. Okay, I don't think there's anything different. Oh yeah, the only thing different about this one is that it's not only asking for the number that happened directly before, it's also asking for the number that happened 2 iterations before. So we're going to be dependent on both the previous and the 2 prior. So I think you're probably going to see the idea, but so we're going to pick it up here within this 3. So I'm going to need the term right before us, I'm going to need A2. And I'm going to need the term 2 before us, I'm going to need A1. Well, A2 was 2, A1 was 1, we crunch it, we get 10. Now let's try again. When N is 4, I'm going to need the term just before us, which was 10. And I'm going to need the term 2 before us, which was the 2. Crunch it down. Follow the same pattern. So when N is 5, A4 is going to be the previous iteration, which was 38. A3 is going to be 2 iterations ago, which was 10. Just keep crunching in this fashion, and here are our first 6 terms. Okay, so we have a more complicated one. Oh, look, yeah, this one requires us to go 3 back. So the recursive formula is telling us we're going to define it based on the previous iterations. So we need a to the 4. So we've got the first 3, so we're going to start with A4. So that's going to be dependent on A3 over A2. See what I'm doing here? Taking away 2 iterations plus A1, going all the way back 3 iterations. So I've got 1 over 1 plus 0 is going to equal 1. Okay, now we're ready for A5. That's going to be the iteration just before us. And then 2 iterations ago plus 3 iterations ago. Whoops, plus 3 iterations ago. So we just need to plug in our numbers here. A4 turned out to be 1. A3 was also 1. A2 was also 1. So this is all going to turn out to be 2. Now I will do one more of these. A6, that's going to be A5 over A4 plus A3. Just follow this pattern. One iteration before, two iterations before, three iterations before. Okay, so A5 was 2, A4 was 1, A3 was 1. So we get 2 plus 1, we get 3. Okay, we could keep going in this fashion, but here's what we're going to generate for the 8 terms. All right, we have I think just one last idea in this section. It's the idea of a factorial. And it just means that whatever you put this exclamation point behind your number, it means you're going to multiply the number 3 all the way times every number down to 1. So this is 3 times 2 times 1. Or 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. And the idea actually comes from, I don't know if you have to call it statistics, but it's the idea of a permutation. And this is the different arrangements of an object. It turns out to be 3 times 2 times 1. Or how many choices that you, let's think of it as arrangements. So I don't need to go into this whole story, but the different ways you can arrange three objects turns out to be 3 times 2 times 1. In my stats video, I'll tell you why that is and think through the logic, but this is all we need for here. So the weird thing is, okay, well 1 factorial is 1 times itself, it's just 1. Why is 0 factorial equal to 1? It doesn't seem to fit or make any sense. And the reason is because this is based on the idea of an arrangement. And so the logic is if you have one object, how many ways could you arrange it? Well, one way. There's only one way to arrange one object. But they extended the idea to 0 and thought, okay, if you have 0 objects, how many ways can you arrange 0 objects? And the logic they came up with is, well, it's still 1. There's one way to arrange 0 objects. There's 0. So that's where that comes from. But just remember, 0 factorial has to be defined as 1. Okay, so we've got some sequences now that are going to involve that factorial, and it's not going to change much. Just got to remember the definition of a factorial. So now we're doing n is 1 in here. So we're going to put a 1 plus 2, so we're going to be doing 3 factorial. And notice how they did 3 times 2 times 1 is where they got the 6. Okay, then we move to the second iteration. We've got 2 plus 2 factorial. Well, this is 4 factorial, so now it's 4 times 3 times 2 times 1. We keep going in this fashion. Now we've got 5 factorial. Just make sure you see what's happening here with the factorial. And that's how we generate our sequence. Okay, so let's try one here. We've got n is 1, or I'm sorry, that's the better. So when n is 1, a1 is going to be 1 plus 1 factorial over 2 times 1. So 2 factorial over 2. So 2 factorial is 2 times 1 over 2 is going to be just 1. Let's do it again. A2 is going to be 2 plus 1 factorial. So 3 factorial over 4. So 3 factorial means 3 times 2 times 1 over 4. So we get 6 fourths, or 3 over 2. Okay, let's go one more time here. So we've got 3 plus 1 factorial over 2 times 3. So we've got 4 factorial over 6. So now 4 times 3 times 2 times 1 over 6. It's going to give me 12, 24 over 6. Turns out to be 4. Okay, we could keep going in this way. I hope that makes sense. We've got a couple more to do, but I think I've got them here. We'll also get 15 and 72. Okay, that's recursive formulas, which require us to depend upon previous iterations, and we also introduce the idea of a factorial.